Welcome, folks. We're going to get started in about a minute. Just going to wait and see if we get one or two more people coming in. All right. Welcome, folks. We're going to get started. Welcome to the 28th day of remote learning. Today's joke: what is the worst joke in the world? This one. Hope you like that joke. I invented it myself, although I'm pretty sure somebody's thought of it before. Couple of announcements before we jump into the math. The first is just a reminder, especially if you are a grade 12 student or a grade 11 student who's planning not to return to Cameron next year, please make sure to go on the school website, click through and sign up for a time to go into the school, clean out your locker, take all of your belongings, and also return your textbooks and Chromebooks. The second reminder is that this summer you will suddenly find yourself completely unable to access anything associated with your Gmail account because it is a school account. Once you are no longer a student in the WRDSB, that account will go away. So if you're in grade 12 or you're moving to a different school board this summer, please make sure that anything that's in your Gmail account that you want to keep, anything that's in your Google Docs that you want to keep, or anything else that is within that Google account is something that you take care of and get a copy out of the account before the end of school at the end of June. I'm not sure the exact timing that your account will be shut down, but you should assume that it will be in early July. So don't wait until like the end of August and hope that things are still there. Get them out now in June, and that way you won't have any trouble. Third announcement: University of Waterloo is running a program for students who are in their final year of high school or in their first year of undergrad. Um, and you don't have to be going to the University of Waterloo to take part in this program, but it's happening in late August. And the idea is to help students polish up some skills before they move into their university studies. So I'll post the information about that in our classroom, and you can check it out if that's something that you're interested in doing. Final announcement for today: marks are now posted in the classroom. If you have any questions or concerns about them, please let me know. It was a pretty unusual, to say the least, process of determining marks this year. Normally, marks are calculated from a significant amount of evidence. This year, obviously, there was not enough evidence to calculate an accurate mark. So I decided that I was going to assign marks based on the high end of what I've seen from students this semester. So if you have any questions or concerns, please do let me know by email. I'm happy to have a conversation with you about that. All right, today's math, we are looking at adding and multiplying functions, and our next few lessons leading into the end of the course will all be on different ways of combining functions. This is one of the most interesting skills of the course, in my opinion, but it's hard to do it until you've talked in detail about all the different kinds of functions. So that's why we've saved it till the end. I hope that you'll enjoy it. The first four, well, really three types of combinations are ones that you're familiar with. So adding, multiplying, dividing, you know how it works with numbers, you know how it works with variables. Now we're doing it with functions. But the final one is a new operation called composition. And when we compose functions, we're essentially taking a function of a function. And there's a whole bunch of mathematical theory that goes from there, and it also has a lot of interesting applications. So that will be our final lesson of the course when we do that. Okay, so let's jump in. Today we're going to do things a little bit differently, bit unusual, in that I'm not going to do it on paper. I'm going to do it on Desmos. There are other streaming services which allow me to stream my screen, but I've not been able to figure out on YouTube how to do that. So we are doing the camera pointed at my Chromebook, a very high-tech method here, but I think it should be good enough for what we need to do. You can follow along. This Desmos activity is linked in the classroom. So feel free to click in. Basically, I'll have you try some things as we go, and you can see what's happening and try it out yourself as I'm working through it here. So that's our deal. If you have any questions, feel free to ask them in the chat. Okay, so the first slide we're looking at here, we're asked which graph matches the function y equals 2 plus 3 to the x. So you know what the function y equals 2 looks like. You know what the function y equals 3 to the x looks like. If we add together those two functions, which of these graphs will we get? And you can go ahead and try it out. Give you about 4 or 5 seconds, think it through. All right. So you probably realize that in this case, we can really think of it like a transformation, right? This is like 3x plus 2, which is going to move the graph of 3x up by 2. And so the typical graph of 3 to the x is an exponential graph. It looks something like this, except that it crosses the y-axis at 1. And if we move that up by 2, then we're going to get this graph down here. All right, so I'm going to keep moving here. So which graph matches the function y equals negative 2 plus 3 to the x? Go ahead, take a moment and try that out. All right, so you probably realize this is like moving the graph of 3 to the x down by 2. And so we're going to get this graph down here. One thing that is going to be helpful as we go through this is to think about this addition of functions as a transformation where we're moving a function up or down. Our usual way is we add or subtract a number, and so we're moving the entire function up or down by the same amount. Once we start adding two functions together where one of them is not a number, neither one is a number, then we're not going to be moving up or down by the same amount everywhere. We're going to be moving up or down by different amounts based on what the function is. So whatever amount that function gives, that's how much we're moving the other function up or down by. All right, so here we can see an example. We have y equals x plus 3 to the x. These are two functions that we know well. Neither of them is constant. So one way to think about this is to think about 3 to the power of x, which has a horizontal asymptote on the left side. It passes through 0, 1, and then it grows very quickly, exponential growth, since it's an exponential function. And we're now going to transform that function by translating it up and down, except that where a translation is moving the whole function by the same amount, here we're going to move it by different amounts depending on what the value of x is. So when I'm out here at an x value of negative 4, the function is going to get moved down. So 3 to the x would normally be just above the x-axis here. It's going to be moved down 1, 2, 3, 4 spots because the value of the function x is -4. Here at -2, the function 3 to the x would have been a little bit above the x-axis. It's going to be moved down 2 spots, 1, 2, because the value of the other function of x is -2. And here, by the time when we get to 0, x has a value of 0. So 3 to the x doesn't change at all. It's not moved. At 1, x has a value of 1. So 3 to the x would normally be at 3. 1, 2, 3. But it's moved up one more up here to 4. And you can follow that through all the way. So we can think of it like 3 to the x has been translated, but it's translated up or down by different amounts. Over here where x is negative, it's being translated down by the x value. Over here where x is positive, it's being translated up by that value. And so the farther we get from 0, the greater the translation up or down, depending on which way we're moving. So hopefully that makes sense. It's a bit of a weird thing, but it is tremendously useful and lets you do some really neat stuff, and kind of breaks you out. I mean, to this point, we've looked at sort of 5 different types of functions. We know linear functions, we know quadratic functions and other polynomials, we know exponential functions, we know logarithmic functions, we know rational functions, we know trigonometric functions. So that's 6. But now we can start combining them. So we can get a much wider array of types of functions from this and types of behaviors. Okay, moving along. So here they're basically talking through what I was just saying, that x has different values depending on the value of x, which is not surprising. So f of x equals x is going to have different values. G of x is 3 to the x, so it's also going to have its own values. And we think of it when we add them as this translation, right? Here's the value of 3 to the power of x. I'm going to translate that by the value of x. All right. So if we add them up, we can go through and have our columns like this, and then here we can add them together, and so we'd get -5.004115223, for example. And you can see there the point appears. I'm just going to do a couple of these. So at -3, we get -3.037037.037. There's our point appearing right there. At 0, we have 1. At 1, we have 4. At 2, we have 9 plus 2 is 11. Oops. Sorry. I'm going to pull this out a little bit so we can see the whole thing. So here we have 1 plus 3, which is 4. Here we have 2 plus 9, which is 11. 3 plus 7, which is 30. And we're already off the screen there. So you can see that shape of the function appearing. So if you're ever looking at a sum of functions and you're unsure of what the graph should look like, this is always an option. You can just make the table and add the 2 functions together and see what values you get for the third one. You can also obviously just graph the combined function on Desmos and see what's going on. But if you didn't have Desmos and you just had a calculator, you could make the table. All right, so we can confirm our graph there. We can see the points we got are on the graph. So now we have a more complicated pair of functions. So we have x cubed plus log x. And so it's worth remembering what these 2 functions look like. So x cubed is a function that is negative on the left side of the y-axis, comes up, curves in towards 0, and then it goes positive on the right side, and heads up to infinity. Log x is a function that starts at 0 and slowly grows. It looks kind of like a square root. Or sorry, not starts at 0. That's a square root function. It starts with a vertical asymptote at the y-axis, comes up, and then slowly grows and looks like the square root function over on the right. So one of the things to think about is what happens to asymptotes, vertical asymptotes, especially when we add two functions. And the answer is asymptotes are very, very, very large y values, right? If we look at the y values of the log function close to 0, if you pick like 0.00000001 log base 10, let's put that into a calculator here. And where is my calculator? Oh, there it is. So we might need a little bit of a lamp here. All right. So if we do log base 10 of 0.0000000001, we're going to get negative 10. And as we get closer and closer to 0, it's going to go farther and farther down. And if we get to the point where we have 300 zeros in there, we're going to be down at negative 300. If we get to the point where we have 8 billion zeros in there, we're going to be down at negative 8 billion. So the asymptote is going to be a large, large number, like negative 8 billion. And as you move closer to the y-axis, it's going to get even bigger and even bigger. And no matter what number you pick, eventually it will get even bigger than that as it gets close to the asymptote. So if we add some number that is pretty small, and x cubed anywhere around 0 is pretty small, to some really big number, the answer is always going to be pretty close to that really big number. And since vertical asymptotes are, by definition, the function going to unimaginably huge numbers, then we are still going to get the function going to unimaginably huge numbers, even if we add or subtract a little bit from that. So typically, wherever you have vertical asymptotes in one of the two functions, you're going to have a vertical asymptote when you add them together. And the only exceptions to that are if one of the functions isn't defined. So if one of the two functions isn't defined, then you just can't do a sum. Or if both functions have asymptotes in the opposite directions at the same place, sometimes they can just perfectly cancel each other out. That is extremely rare. We're not technically supposed to talk to you about it in advanced functions, but I like to give you the fuller story. So if we're looking at this, we say, okay, log x, that's got a vertical asymptote going down at 0. So I know that I should have that. And in fact, all three of these graphs do. The other thing we know about log x is it's not defined for any negative numbers. Well, let's say we look at negative 1. Negative 1 cubed is negative 1. Log of negative 1 is undefined. What's negative 1 plus undefined? It's undefined. So the combined function is not going to exist anywhere where one of the two functions doesn't exist. So this whole negative space, we would expect the function doesn't exist. So that lets us eliminate this one. It can't be right because it's defined in the negative x values. So it's down to these two. And one of the things we know is that log x, as we go to positive numbers, it doesn't grow very quickly. It's kind of small numbers for a long way. But x cubed does grow very, very quickly, right? By the time we get to 10 as our x value, x cubed is up at 1,000. So it's growing really fast. So we would expect that we would see quick growth here, kind of like this one, not slow growth like that one. For example, when we're out at 10 here, log base 10 of 10 is 1. But 10 to the 3 is 1,000, so we should be at 1,001. This clearly is not. So it's got to be this graph right here. Okay, And so we can again go through and do the adding and so on. I'm going to let you do that on your own time, just in order to save time and make sure we get through this. But feel free to come on back and try those out. And then we can confirm it here. And you see that we do indeed have the graph that we picked. Okay, select the graph of the function y equals cos 2 pi x plus x squared. So I want to take a brief side note here and just talk about cos 2 pi x. If you'll recall, the period of cosine function, if it has a transformation here in front of the x, is to do 2 pi divided by whatever this number is. And 2 pi divided by 2 pi is 1. So this transformation is just making it so that the cosine function goes through an entire period in a distance of 1. And you can see on the graph here, from 0 to 1, the cosine has gone through exactly 1 rotation. And we are getting period lengths of 1 for the rest of these as well. You can see that all of the maximum are correspondingly on an integer value. This, it's hard to see here. You can see it better here. Each block is worth 2. So you're going to have a peak at 0, a peak at -0.5, a peak at -1, or a peak halfway through the square because that's where -1 is, and a peak all the way through the square because that's where -2 is. And here again, you'll see all of the peaks corresponding to integer values. Okay, so which one of these is going to give us cos 2 pi x plus x squared? Well, we know that neither of these have vertical asymptotes, so we shouldn't see any vertical asymptotes, and we don't. These are probably turning around and coming back off the screen, so they're not actually asymptotes. It's just that our view is too zoomed in to see them. And we know that x squared goes up to the right on both sides. And most crucially, for me at least, when I'm thinking about this, is that I know that cosine never has a value above 1 or below -1. So for me, I usually think of this as like, oh, cosine is the small function. It's never bigger than 1, never negatively bigger than -1. X squared is the big function, right? X squared of 10 is 100. So x squared can get to big numbers fast. So this graph should look like x squared with some small changes that follow the pattern of cosine. And if we look, this looks exactly like a cosine. There's no evidence of x squared in here. This one looks pretty weird. It's not like x squared. X squared should be shooting up here on the right, and this function is not. This one looks like x squared in its general shape with some waviness from the cosine. And that's what we'd expect, that here at 0, x squared is 0, but cosine is 1. 0 plus 1 is 1. So we pushed the x squared graph up by 1. Here at a half, which is halfway through the cycle of cosine, it's down to -1, but x squared is at a quarter. So we've taken a quarter and we moved it down by 1. At 1, x squared is 1, cosine is 1, added together there at 2. And so you can see it's pushed x squared up by 1, move x squared down by 1, pushed x squared up by 1, and so on. And so it follows the pattern all the way through. And so we can tell that this is the function that we want. All right, and so once again, you're welcome to go through and do the graphing with the tables. So there's a handout in the classroom, and I'll invite you to take a look at it. 4.13.h, I guess I should give it a better title. Characteristics of sums and products of functions. And if you take a look at this, you'll see that we have some questions about adding two functions together. So the first question is, where will a sum of two functions have zeros? And the answer to that is wherever the values of the two functions are negatives of each other. So if one function has a value of 5 and the other has a value of -5, when you add them, unsurprisingly, you're going to get a 0. So that is the answer. Where will h of x have zeros? H of x will have zeros where f of x and g of x have values that are negatives of each other. So where will h of x have vertical asymptotes? And if I'm talking too fast, feel free to just pause the video and fill it in yourself. So where will h of x have vertical asymptotes? It will have vertical asymptotes wherever one of the two functions has a vertical asymptote, mostly. And so as I explained earlier, if the two functions have vertical asymptotes in different directions, they may cancel out, not always, but they may cancel out. Or if one of the functions has a vertical asymptote, but the other is undefined, then the sum will be undefined rather than producing a vertical asymptote. But in general, most of the time, f of x plus g of x has a vertical asymptote wherever one of the two functions has a vertical asymptote. Okay, and 3, what can we say about the direction of approach to the vertical asymptote? In other words, is h of x going up to the asymptote or is it going down to the asymptote? And in general, it is always whatever the individual function was doing. So if f of x has an asymptote where it goes up to the asymptote, can't really see an example here, but let's say we have an asymptote here and we're going up to it. Doesn't matter what g of x is, that as long as the asymptote is being caused by f of x, it will be upwards. So the other function doesn't change the direction of approach to the vertical asymptote. It just leaves it the same no matter what the other function is, unless it's enough to cancel out the asymptote. All right. So moving back to the Desmos, and again, I am trying to keep an eye on chat here. I'm not seeing any questions, but if you do have questions, feel free to type them in there and let me know. So moving back into our Desmos here, we have now a multiplication of functions. So multiplications of functions are often a little bit easier to think about and to detect than additions. And one of the reasons for that is that we know from way back in grade 10 when we were solving quadratics that if you have two things multiplied together and one of them is 0, the overall product is 0. And so that's the case here. X has a 0 when at 0. So f of x equals x. F of x is going to be 0 when x equals 0. G of x equals 3 to the x doesn't have zeros anywhere. So when we multiply them, there should be a 0 at 0. And if we look at this graph, it doesn't have one. If we look at this graph, it doesn't have one. If we look at this graph, aha, it has one. So we have a 0 at 0. The other thing besides that the multiplication of functions has a 0 wherever either function has a 0 is that the sign of the function is determined by the sign of the two individual functions in a very typical way. So if one is positive and the other is negative, the overall is going to be negative because positive times negative makes negative. So 3 to the x is positive everywhere. X is positive on the right-hand side of the y-axis and negative on the left-hand side of the y-axis. And so if we multiply that by a positive number, that's not going to change. And so the combined function should also be positive on the right-hand side of the y-axis and negative below the x-axis on the left-hand side of the y-axis. And that's exactly what we see here. So we're getting this shooting up on the right. We're getting it going to 0 on the left. This one, I'm again not going to go through and do the table, but for this one, I would strongly encourage you to do the table. And one of the reasons is that one of the things you'll see is how the exponential function dominates the linear function. So in this negative space here, on the negative side of the x-axis, the exponential function is getting close to 0, while the linear function is going off to infinity. So there's kind of this battle happening when you multiply them together. One of them wants to get really big, and one of them wants to get really small. And so there's this question of, well, which one is getting big or small faster? And I'll put that in air quotes because we haven't defined what that means right now, although you will in university. So one of the ways, or the easy way for you to see it, is to actually do these multiplications. And you'll see very quickly that the exponential function is going to 0 much faster than the linear function is going to infinity. And so their multiplication is going to be very close to 0. It's going to go towards 0. All right, so I do recommend that you graph that, and here you can see the exponential function dominating and pushing the multiplied function to 0 instead of letting it go down to negative infinity. And you can actually see that for a little bit here near 0, the linear function wins, and it starts to push away from 0, but very quickly the exponential function takes over and pushes back towards 0. All right, so 2 to the power of x times sine 2 pi x. So the 2 pi in here again is just changing the period of sine to be 1 instead of 2 pi. So I really like graphs of trigonometric functions, sines and cosines in particular, that are multiplied by another function. They do really neat things, and what you can think of this as is that this sine function is being scaled, so it's being expanded or compressed by the other function. And since the other function isn't constant, that means in some places the sine function will be expanded a lot, and in other places it will be compressed a lot, depending on the values of 2 to the x. So 2 to the x goes close to 0 as we go negative. And so you can see in this first graph, which we'll see is the correct one, sine has been compressed down, and it's still waving up and down. It's just being compressed smaller and smaller and smaller. Its amplitude is getting tiny because its amplitude is defined by 2 to the x, and 2 to the x gets really tiny as we go off to the left. On the other hand, as we go to the right, 2 to the x grows really quickly. And so our sine function's amplitude is going to grow really quickly, and you can see that happening here. If you enjoy music and you've done any audio editing on a computer, you'll know that fading out is one of the things that's really common in audio editing. And if you wondered ever how do computers calculate a fade out, this is exactly what's happening when there's a fade out. The wave function of the sound is scaled downwards by some other function that decreases to the right. And so you get the volume going from loud to quieter to quieter. You probably don't want to use 2 to the x for your fade outs because it will fade out the sound very quickly. And people will barely be able to hear any fade at all. It'll almost sound like it just cut out. But you can pick other functions that decrease to the right to use for your fade out. And those of you who've worked extensively with computer audio tools will know that some of them even allow you to type in the function that you want to use for the fade out. All right. So zeros, we talked about it. We said this is going to have, it's a multiplication. So where either part of the multiplication is 0, the overall is going to be 0. 2 to the x has no zeros, but sine 2 pi x has lots and lots of zeros. It's going to have zeros at 1, 1/2, 2, 2.5, 3, 3.5, and so on. So every integer or half integer, this function is going to have zeros. And then you can go in and do it graphically. That's a fun one to do. Here you can see a little bit better the behavior that we're looking at. where the sine function is just scaled up or down by 2 to the x. And if you just plotted the top end, the peaks of the sine function, and you didn't show anything else, and you ask somebody, what graph is this? They'd say 2 to the x, and they wouldn't be wrong, because the graph of 2 to the x, I'll see if I can add it here, y equals 2 to the power of x. There we go. When sine has a peak, its value is 1. So if you multiply sine by 2 to the x at its peaks, you're going to get 1 times 2 to the x, which is 2 to the x. So at the peaks here, this is literally the same points as 2 to the x, but everywhere else, the multiplied function is affected more by the sine. And you can see that it needs to go negative anywhere sine is negative, because 2 to the x is always positive, and positive times negative gets us to a negative value. All right. So I'd ask you to try the rest of this on your own. I'm not going to work through it with you. It's something for you to try, preferably before you dive into the textbook questions. So it'll give you some nice opportunities. I want to finish filling in the handout 4.13H from the classroom. We did the first 3 questions about sums, and now I want to answer the last 3, which are about multiplication. So the first question is, if you have a multiplied function, f of x or h of x equals f of x times g of x, where will h of x have zeros? It will have zeros where either f of x or g of x has a 0. So if either one has a 0, then your combined function has a 0. As always, there are some slightly tricky situations. And for this one, the only situation is if one of the functions has a 0 and the other function is undefined. And so again, anywhere that either function is undefined, the multiplication of them will be undefined. And there are no exceptions to that. We can't multiply undefined by a number and get any answer other than undefined. It's always, always, always undefined. So if you have f of x equals 0 and g of x equals undefined, and you multiply them together, your answer is going to be undefined. So that's the exception to the rule that where one function has a 0, the other one, or the multiplication, will have a 0. For vertical asymptotes, again, where either function has a vertical asymptote, typically the multiplication will have a vertical asymptote. And I don't believe there are really any exceptions to that, except if one function has a vertical asymptote and the other one has a 0. Depending on how it approaches the 0, you could get the cancellation of the vertical asymptote, but that would be quite unusual. So most situations where we have vertical asymptotes will stay as vertical asymptotes. And so 6 is the question that's a little different, or more different, I guess, from multiplying functions to adding them. So when we were adding functions, the direction of approach to the vertical asymptote was just whatever the original function with the vertical asymptote had. For multiplications, then we need to actually look at the signs of the two functions. So if one of the functions is approaching a vertical asymptote positively, so it's going up and up and up very quickly, but the other function is negative, when we multiply them, we're going to get positive times negative, which is negative. So the function is actually going to negatively approach the vertical asymptote for the combined function. So that's the thing to be aware of, is we have to look and see what are the signs of the two functions and what product do those signs make. And that will tell us whether we're going up or down. All right. So that's it for today. I hope that you've enjoyed that. Give it a try. Please try finishing off the Desmos activity. Hopefully it will be of use to you. And there's some interesting things, and you can begin to play around a little bit. You can make some wicked cool looking graphs playing around with these combinations of functions. So I'd encourage you to have some fun with that. Have a good rest of your day. If you have any questions, please send them to me by email.